right, section 4.4, we have one of these sort of mathematical titles that says the fundamental theorem of. Anytime you hear the fundamental theorem of in math, it's really important. Sounds important, right? It's fundamental, okay? So in counting principles, right, I have a class right now, we do the fundamental principle of counting. Here we have the fundamental theorem of calculus. There's a fundamental theorem of algebra. People like to put the fundamental theorem of in front of things. It's really important. It pulls the rest of the pieces together that we haven't so far in chapter 4. And it does so right away. This is the fundamental theorem of calculus. It says, if f is continuous on a closed interval AB, and capital F is any antiderivative, remember that's our notation that we encountered in section 4.1, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a. So since we just finished that last one where they gave us some pieces, I'd like to take a look at one of them with you. I think it said, this was given to us on the last problem, okay? So we're going to hope that it's true. Did I get it in there right? Oh, is it x cubed? Sorry, x cubed. That makes more sense. I might have typoed it on this other slide wrong. If I did, I apologize. X cubed. Okay, so what this theorem says I can do is I can take the antiderivative of x cubed. You've been practicing that because you have a gateway coming up, right? What is the antiderivative of x cubed? X to the fourth over 4, or with a 1/4 in front, right? I recognize that there's a plus c. I'm going to write it in on this one, and you're going to very quickly find out that you're not going to have to do so when you have definite integrals, but for the moment, we're going to write it in, okay? This is the general antiderivative. Agreed? Yeah, it is. What this theorem says I can do is I can take this general antiderivative, and I can evaluate it at 4. That's what this means, right? And then I can evaluate it at 2. Now, the notation that we see used is there's a vertical bar that's drawn at the end, and there's a 2 at the bottom and a 4 at the top. We're just sort of shifting it from the left side to the right side. And what this is saying is that I'm going to put the number 4 into this. So I'm going to have 4 to the 4th over 4 plus c. And I'm going to subtract putting the number 2 in. So 2 to the 4th over 4, plus c. Okay, so let's talk about the c's real quick. What's going to happen to my plus c's? They're going to cancel out. I have a plus c in both of them, and there's a subtraction sign in between. That always happens. What that means is that when you're working with definite integrals, you don't have to do plus c's. If you're doing general antiderivatives, i.e. gateway on Friday, you got to have the plus c because you're not putting numbers in ever, okay? But if you're evaluating with numbers in, you don't have to do that. So let's find these values. What's 4 to the 4th divided by 4? 64. So the first one is 64. What is 2 to the 4th divided by 4? 4. And what is 64 minus 4? 60. This is how the process works, and it works like this all the time. And I was just verifying one of the facts that we were given and told, just take it for what it is and don't question it. Well, it's true. We just showed that it worked, and the other two would have worked as well. So we're going to do some examples with this, okay? So this is a really good section for us to be doing because it's going to practice those general antiderivative skills that you're going to be quizzed on Friday. And then we're going to do this extra piece at the end where we do some evaluation. Now, as we do this, I want to show you some cool calculator tricks too, because I think that's helpful. You're not going to plug any numbers in on Friday, so this part doesn't apply, the calculator tricks, and you won't have it. But we're going to first do exactly what the fundamental theorem says, which is take an antiderivative. So first piece at a time, or one piece at a time, first piece, negative 3x. What is the antiderivative of negative 3x? Okay, this is what Adrian said. Do you agree? Yeah? Wonderful. Somebody else, what's the antiderivative of the plus 4 part? Yep. Avery said plus 4x. That's correct too. Okay, everybody good with that? If this is all we were doing without limits, we'd need a plus c, but we don't need that because we have our numbers, so we don't put plus c. If it bothers you and you just want to never forget, feel free to do it. It's going to cancel out anyway later, but you don't need it. Next, we're going to do a vertical bar, and we're going to write down the 2 and the 5. Okay, so everything I've shown you so far is exactly what I would expect to see when you're looking at a quiz question or a test question. This part is all of what we're showing. Then you're going to show that you're putting the 5 in. Okay? So we're going to have negative 3 times 5 squared over 2 plus 4 times 5. And all of that subtracts, doing the same thing with 2. So negative 3 times 2 squared over 2 plus 4 times 2. After this point, if you want your calculator to do the arithmetic, that's cool. All right, we're not in the junior high math class where I need to see your arithmetic written out, or elementary. Okay? But I expect to see these pieces. Why? Because this is what the fundamental theorem told you to do, and I'm trying to make sure you understand the fundamental theorem. Are you with me? So let's do a couple of things on our calculator to show how we could do this. The first option is going to be very directly like what it looks like on the screen right now. So I want you to put into your calculator the antiderivative part that you got. Okay, so we're putting in the antiderivative, not the original one. Let's try this again. That's not working well, is it? Let's try this again. That one. It's just not going to go to my screen. That's fantastic. Okay, something's disconnected. All right, we'll just talk through it, and I'll move around, and hopefully the calculator will solve it, deal with itself. Okay, so take a look. So we can put a negative 3x squared over 2 plus 4x. That's what should be in y1. Does everybody have that in y1? Okay. Negative 3x squared over 2 plus 4x. The same thing we got. All right? And then back in your regular screen. So go back to the regular blank screen where you can add, subtract, multiply, and divide. I want you to do vars. We talked about this before from a different perspective. Vars, y vars, function y1. Put a parenthesis and do 5. Minus vars, y vars, function y1, and do a parenthesis of 2. So in your screen right now, it should look like this in the regular screen. Is everybody doing that in the regular screen like it looks right? Okay, we're about to find out. Press enter. What does your calculator say this value is? How much?
Negative 19.5.
Good. Negative 19.5. Joshua said it right. Does everybody else say it right? Does anybody not give you that value? Because if it doesn't, I want to see your picture real quick. Yours okay, Tanner?
It's just a fraction.
Okay, yours turned it to a fraction. That's fine. And a fractional answer would be acceptable too. I don't have any problem with that. Okay, is everybody good with this? But are you ready to see something more fun? Like, of course, right? Okay, I want you to go back to your y equals. Clear it out. I want you to put the original function in. Okay, so the original one was negative 3x plus, negative 3x, plus 4. Okay, so original equation into y1. I want your window to be just that negative 10 to 10 window. Okay, so zoom 6 is the standard window, or you can go negative 10 to 10, negative 10 to 10, and graph it. And it's It's a graph that looks something like this. Okay, does everybody's graph look something like that? Okay. So if you were to look on this graph, the 2 is a little bit after where this crosses. It's about right there. And 5's a little further. Agreed? That's, sort of like roughly where those values are. I want you to hit the second trace button. So second trace brings up a menu that says calculate. Do you see a menu that says calculate when you hit second trace? Okay, do you see number 7? Number 7 should look like the notation we've been using. It's got a little script as, f of x, d of x. Do you see that? Either press number 7 or arrow down and hit number 7. Now when you do, on your screen, on the left-hand side, or in the bottom left corner, it says lower limit. Does everybody's screen say lower limit in the bottom left-hand corner? Okay, our lower limit is what? 2. Just type the number 2 and press enter. And then it says upper limit, and our upper limit is 5. Press 5 and hit enter.
Holy crap.
What happened? 2 things happened. What happened?
Shaded.
It shaded it in. And also, what do you see in the bottom left-hand corner right now? The answer, right? That's pretty cool. Now what that means is that you can get the answer without ever doing the calculus, right? Which also means that the answer doesn't give you a whole lot of credit if you don't show me the calculus. Yeah? Yeah, and your calculator is doing this with numerical processing, so it might actually, in some cases, maybe not on this one, not say negative 19.5. It might do something like this. Negative 19.4999999. Did anybody do that on this one? No? It usually does it on ones that aren't linear. This one's linear, okay? But that's a very cool trick, isn't it? Here's the catch. Your window has to include those x values. So if my window had not gone from 2 to 5, which that's why I told you specifically make sure it went from negative 10 to 10, then it wouldn't do it. It would give you some kind of an error. Okay, there's one more way that you can do this. So go back into your regular screen again. Okay, regular screen where we did the y1 of 5 minus y1 of 2. I want you to hit math. Okay? If you go all the way down past where it is right now, math 9 says FNINT. Do you see that? Okay, that stands for function integration, FNINT. So if you select that, I have an older operating system, so mine actually shows up on my screen right now saying FNINT. Probably most of yours actually shows up with things that look like this. Okay? So out of curiosity, does anyone's calculator look like mine where it says FNINT? Okay, then I'll show both of them. Okay, so I'm going to talk to you two first since my screen's up that way. For FNINT, it has parentheses as well. You hit vars y vars function y1, and then you put a comma. There's a comma on the screen under the sign button. Then you put an x. You put a comma, and you do your lower limit, which for us is 2. And you do your upper limit, which for us is 5. You press enter. Okay, all this is telling your calculator is my function is in y1. The variable for my function is x. My lower limit's 2, my upper limit's 5. If yours looks like this, it's going to mirror what we did before too. I'll change colors. So you're going to put a 2 down here. You're going to put a 5 right here. You're going to hit the vars, y vars, function y1 there. And you're going to put an x here. Notice it's all 4 of the same pieces. They're just put into it visually the way it's showing up. And once you do so, if you press enter, it should still also tell you negative 19.5. Now it doesn't have the cool picture. You get it, you give a little bit for that. But you didn't have to worry about the interval actually showing up on your calculator screen, right? We don't have to worry about that. This will work for any interval we wish. So there's really no reason not to have the right answer on these, because you basically have a technique with your calculator to do it. Okay, so let's go on to the next one. But these are the cool calculator tricks that we can do on each one of them. Okay. So number 2, we do have some trig. And number 2 is an example of one that the calculator will not do us very well for, because it's going to give us an approximation, and we can by hand find an exact value. So this is one of those catches where it doesn't work great with the calculator. All right, so we have an integral from 0 to pi of 1 plus sine x. What's the antiderivative of 1? X, or 1x, yeah. Whoops, back to my black. What's the antiderivative of sine of x? Yeah, it's negative cosine of x. Be careful on those signs as you're studying and preparing for Friday. Remember which ones are negative and which ones are positive. It would be a sad thing to miss a problem on a negative, wouldn't it? It happens all the time, so just be careful. We're going to do our limits of integration. That vertical bar is 0 and pi. And we're going to put the pi in first, right? We always put the upper one in first. So I have pi minus the cosine of pi. And then minus 0 minus the cosine of 0. Unit circle stuff. It keeps coming back, doesn't it? It's like a haunting feature. What is the cosine of pi? It is -1. Okay, and if you're still picturing the unit circle, it should be picturing something that looks like this. That's a fat unit circle. Let's try it a little thinner. That's better. The cosine value, so if we're at pi, we're over here. Cosine value is the x value, so it's -1. So this is now pi minus -1 minus, well, there's a 0 here. I'll write it in for just a moment. And then what is the cosine of 0? Well, 0 is over here. What's the cosine value at 0? It's actually +1. So this is minus, because it's in the formula, right? It came from here. And then the cosine of 0 itself is a 1. I'll put it in parentheses, though they're not necessary. Okay, the reason your calculator is not going to be real great at doing this is because there's a pi in here and it's irrational, and it won't turn things back into rational numbers when they start out irrational. It doesn't do that. So the pi doesn't get simplified. So this is pi plus my 1, because I've got a -1. And then over here I also have -1, so it's another 1. So my answer is actually pi plus 2. Now, you should know what that is approximately. What is that approximately? Should be about 5.14. So you can use your calculator to confirm that you did it right. There's nothing wrong with that. But you can't use your calculator to find it and then turn it back into the pi plus 2 very well. Especially if we had something that was more complicated, like pi's over 3s or something like that going on. Like it would be messier. Okay, so I'm going to avoid using the calculator, but feel free to check it if you would like. This is the right value. Okay, there is another fundamental theorem of calculus. It's called the second fundamental theorem of calculus. And it's an interesting one because it's super intuitive. Like, it's very obvious because we do this with other operations all the time. Here's what it says. It says f is continuous on the interval, closed interval AB, and capital F of x is an antiderivative of little f of x. Okay, it's the same setup that we had on the first fundamental theorem of calculus. But the part at the end that's underlined tells us if I take the derivative of the antiderivative, I get back to the original function. In other words, what it's telling us is that derivatives and antiderivatives are inverse operations, right? If you multiply by 3 and then you divide by 3, you get back to where you started. My grandfather, he passed away just a year and a half ago, I think, and he was around when email first started coming out. Some of your grandparents might be in this same boat as mine was. And he was really intrigued by all these things. And he was intrigued by the things that came out, which they come out on social media now too, where they say things like this: take your birthday, multiply by 2, and then multiply by 6, and then subtract your age, and you get some mysterious number. And he was like, whoa, how did that happen? And I'm like, it's math, right? It just gave you a bunch of inverse operations. You just didn't recognize them along the way. That's all this is. It's an inverse operation. That's it. There is a caveat to it, and we'll see it happen in an example. The caveat is what happens when we have a chain rule. Okay, so we'll see that happen. But let's take a look at one. I think the first one we have is a pretty straightforward one. Yeah. Okay. So let me make one more mention. I didn't sort of say it. Notice the upper limit of integration on everything on this screen. It's not a number, right? It's the variable x. Are you with me? So when we have the variable x, what's the derivative of x? It's 1, yeah? So we sort of lose the uniqueness of what happens because its derivative is just the number 1, and you multiply by 1, it sort of disappears. It sort of looks like it's not there. On this one, my upper limit's not 1. It's the sine of x. So I'm going to do this problem 2 ways. I'm going to do it the long way, which you can do every single time if you wish. And then I'm going to do it the short way using this theorem, and you can see how it shortens it up and how it makes it helpful, like how this theorem's helpful. Does that sound fair? Okay, so if you don't like my shortcut at the end, and you may not, like legitimately you may not, you can always do it the long way. Okay, so what is this saying we're going to do? Well, we're going to actually find an antiderivative to start with. Okay, we're going to do the problem as it's outlined, ignoring the directions at the top. We'll come back to them in a minute. We're just going to find the antiderivative. All right, so what's the antiderivative of t? T squared over 2. What's the antiderivative of 2?
2x.
Yeah, 2x or 2t, since t's in this particular problem. Yeah, 2t. As long as you make your variables match, I don't care. WebAssign will care. If you change t's to x's, it won't like it. Okay, so just pay attention if they've used a different variable. We're going to do our limits of integration. It's going to say sine x on top and 0 on bottom. Now, it's also probably worth noting that the number on bottom that it's listing here is any number, so there's nothing special about what that number is, and you'll see why when we get to the part of it here in a minute. Ours happens to be a 0. That's fine. So we're going to evaluate this at sine of x. So now I have sine of x squared over 2, or you can put a 1/2 in front if you wish, plus 2 sine of x. That's putting the sine x in. Then I have minus 0 squared over 2 plus 2 times 0. Okay, evaluation look okay? A little different than the ones we did before because it got sine x in there, but the process is still the same, right? So we're going to clean it up a little bit. In particular, this second bracketing piece, what's it equal to? It's 0. So this actually just ends up being, I'm going to put my 1/2 in front, 1/2 sine squared of x, feel free to leave it over 2 if you'd rather, plus 2 sine of x. Okay, that's what it is. This is f of x. That's what we found. We found f of x. Now, that's not what we were asked to find. What were we asked to find? The derivative of that, right? We were asked to find the derivative of that. So now we're going to find the derivative. We took the antiderivative. Now we're going to take the derivative of that value. Okay, so this is where that chain rule that I sort of alluded to comes into play. You have a 2 up there on a sine of x. So I have an inside function that's sine, and I have an outside function that's a power, right? Everybody with me? If you prefer to have it written this way, we can actually write it like this as well. It's the sine x quantity to the power of 2, if it's a little bit more obvious like that. So we have to do a chain rule, right? Derivatives. Now I know we haven't been doing derivatives for, this whole chapter. Now we need them. So we're going to take the 2 and we're going to pull it down in front. And it's going to get multiplied by the 1/2. I'll write it out, but feel free to not write it if you don't need to see it. We rewrite the inside, which is sine x. Sine looks like an 8. There we go, sine x. And then with the chain rule, I have to take the derivative of sine x now. What is the derivative of sine of x? Cosine of x. Okay, is that part okay? Pulled the 2 down, rewrote to the power 1. Right, because that's what we left. And then derivative of sine's cosine. I'm going to do the second part. Plus 2. What's the derivative of sine? Cosine. Okay? This is the answer. All right? This is the answer from the long way. So let's figure out what happened if we're thinking about it from the original piece. Notice, it started out saying t plus 2. Well, I shouldn't have this written here. Let me actually at least delete these 2. The 1/2 and the 2's cancel. We'll take them away. Okay, a little bit of cleanup. Well, this doesn't look like t. And there's a 2 here, but there's also a cosine. What happened? Here's what happened. You draw a line. Actually, let me move this over. What you do is you take the t plus 2. And you evaluate it at the sine of x. Okay, that part's okay. So this is sine of x plus 2. But then you have to multiply that by the derivative of sine of x. What is the derivative of sine of x? Cosine of x. So if I distribute my cosine of x in now, what will happen? What happened? It's the same thing we got before, isn't it? It's this. But it didn't take near as much work. I didn't take any antiderivatives at all, in fact. The only derivative I took was the derivative of the sine x itself. There's no chain rules. None of that happened because what I really did is I did an antiderivative and I did a derivative at the same time. And then I recognized that because I don't have x on top, I've got to multiply by the derivative of x. In this case, the derivative of sine x. That's cosine of x. Okay, if this is confusing you, if you don't like it, just don't do it. You can always use the other process. It's just going to take a little bit longer. Okay? Now, sometimes they're a little bit more direct. This next one actually, in some ways, is a little bit more direct. In some ways, it's not as well. But let me show you what happens. First of all, notice on this one that I do not have a constant on bottom or on top. At least over here, I had a 0 on the bottom, right? And this theorem says I'm supposed to have a constant on the bottom. Yeah? Yeah. So the first thing to do is to fix the fact that I don't have any constants. And we do that using a property that we saw, it was in the last section, so I can't go back to a slide. It said that if you go from A to B, you can pick a point in between, remember? And you can split it up into 2 intervals. That's what we're going to do. So we're going to rewrite this as x2, and you can pick any number you want. It doesn't matter, so I'm just going to pick 0 because it's easy. But you can pick any number. T squared plus 4 dx. And then I'm going to start at 0, and I'm going to go to the upper limit of integration as given, 3 minus x. T squared plus 4 dx. Okay, so far so good? Literally what I did is I said my interval went from x to 3 minus x, and I said there's some value in between them. I called it 0. It doesn't matter if it's 0 or not, but there's some number in between it, and so I split my interval apart. Okay? Now, this first piece looks almost like that. What's wrong so far? What part doesn't make it look like that? Say it, Tanner. The interval's flipped. On this screen, the constant is at the bottom, and on my problem, my constant right now is the top. Again, that's a property we just encountered in 4.3. I can flip it, but if I flip it, what do I have to do? I have to make it negative. So I'm going to flip it and make it negative at the same time. Okay, is that okay with the first piece? I'm turning it into something that looks like that other piece. Now, the second one is actually in the right order. It's all good. So what I want to show you is how lovely the fundamental theorem works when everything is used that's in it. So here's what I have right now, just rewriting it. This first piece, except for the negative in front, perhaps, whatever, looks exactly like that screen before, right? And that screen said what I can do is I can simply take the integrand, t squared plus 4, and I can replace the t with x. Now, there's still a negative in front, but the t gets replaced with x. This is x squared plus 4. Simple, quick, easy. And the reason I don't have to worry about chain rules is because what's the derivative of x? 1. So if you wanted to sort of be aware of it and just write down times 1, that's okay, because the derivative of my upper limit of integration is 1. The next piece, I'm going to do the same thing. The t squared, the t part of it, is going to be replaced by the upper limit of integration, the 3 minus x. So this is 3 minus x. It replaces the t plus my 4, like this, right? So the t squared is being replaced by the 3 minus x now squared. And then I need the derivative of this upper limit of integration. What's the derivative of 3 minus x? Negative 1. Okay, didn't take any antiderivatives. I really only took one derivative, and it was a really quick and easy one. And we're just going to clean up what's there. Okay, so I'm going to distribute the negative through this. This is negative x squared minus 4. Over here, I need to distribute this out, right? This is foiling. You can't just square the 3 and square the x. That's a no-no. Yeah? We're going to square all of it. So when you square all of it, you get 9 minus 6x plus x squared. And you have plus the 4 at the end. All that's times negative 1. We're going to clean this up in the middle and distribute the negative 1. I think we can probably do that all together as one step. So I'm going to do it that way. I have the 9 at the beginning. I have the 4 at the end. That's 13. But the negative at the end makes it minus 13. I have the negative 6 times negative 1. That's going to make it positive 6x. And then I have the x squared in the negative, so that's going to make it negative x squared. Combine like terms. There's negative 2x squareds. I have a positive 6x. And I have a negative 17. Indeed. That's how the fundamental process works. Okay, are we good? All right.